Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Stephen Feuerstein, and I'm a PL/SQL developer just like you. This lesson is part of my series on programming with collections, the array-like structures of PL/SQL, which I would consider to be one of the most important foundational features of the modern PLSQL language. You can't take advantage of most of the great stuff in PLSQL unless you know about and can work with collections. The focus of this lesson is non-sequential indexing and associative arrays, a relatively advanced topic, but one that can give you lots of incredible benefits as you write your applications. Some quick reminders. If you haven't already done so, visit toadworld.com/sf, otherwise known as PL/SQL Obsession, where you can download all the scripts that I'll be using in this lesson and my other lessons, as well as supporting PowerPoint documents. So here's PL/SQL Obsession, lots of resources for PL/SQL developers. Here's the demo zip download that contains all the scripts that I use in my trainings. And if you drill down to training seminars and presentations, you'll find PowerPoints supporting these lessons. Second, make sure you're comfortable with the material covered in the previous lessons in this series. Make sure you understand what collections are, the different types of collections, using collection methods, and most importantly, working with associative arrays. But just in case, let's start with a quick review of associative arrays. An associative array is one of the three types of collections in PLSQL, associative arrays, nested tables, and V-arrays. And associative arrays, or the type of associative array that you use to define and work with collections of type associative array, follow this form. You provide the name of the type, is table of, meaning is a collection of or list of elements. Each element type here is a last name of the employee's table. It could be a record, another collection, just about anything you want. And then the index by clause, and this is specific to associative arrays. Only associative arrays specify an index clause. In this case, I'm saying index by integer. I can also index by string, which is the subject of another lesson, string indexing of associative arrays. And we're going to be focusing on using this index inside the collection and what some of the challenges are in doing so, and how you can take full advantage of this indexing. So, list of elements. A collection is a list of elements accessible via the index value. So if I know the index value of 16, I can go directly to that point, that element in my collection. Indexes can be integers or string, which means you can essentially index by anything you want. But index values can never be null. And most importantly for the topic of non-sequential indexing, associative arrays can be sparse. This means that, let's take a look at this example. Let's suppose I have a list of strings. They happen to be the names of fruit. So apple is in position or index value 1, pear is in index value 22, orange index value 100, and apricot 10,023. Notice I have not filled sequentially from 1, 2, 3, 4. I can do that, but I don't have to. I can populate elements in non-consecutive index values. And that's the focus of this lesson, and one of the reasons that it's so useful is that I can use it to easily emulate primary keys and unique indexes. And more generally, anytime I have an index value, the mechanism by which I want to look up elements in my collection that are not sequentially allocated. Just a couple of comments on this index by. So with associative arrays, you specify the indexing, and the idea behind that index is the same as an index in a relational table. It gives you an ability to very quickly look up elements in the collection without having to scan through all the elements. So just like with a relational table, you want to avoid full table scans. The same thing is true in collections. You want to use the index to quickly find the element in your list. Let's take a look at non-sequential indexing and why you might want to use it. Certainly sometimes you simply want to add items to the end of your list. In other words, add them sequentially and consecutively. And this makes sense certainly if the order in which items were added is significant. I need to know that the third item chosen is ABC. So I can go to location 3, get ABC, and that tells me that that was the third thing chosen. But that's not always the case. And particularly sometimes, even if the order is significant, sometimes I need to find a specific element in the list, not by the index value, not by the order in which it was added, but perhaps by a string or a date. I'm going to look up all my employees in my list. I want to find the employee with a certain last name. Well, with sequential indexing, I have to scan through the kinds to find a match. And certainly, I might want to find elements in my collection with more than one index value. I want to find an employee by employee ID. I want to find an employee by last name and first name. I want to find an employee by their social security number. But the challenge there is that collections can have just one index. It's not like an Oracle relational table where I can simply create multiple indexes on my collection, thereby on my table, thereby enabling faster access to those specific rows using different pieces of data to find them. And there's no way you can get around that. The collection has just one index. Let's take a look at what is involved when you do sequential allocation, and then you have to scan through a collection. Then we'll take a look at using the non-sequential indexing to avoid this. So String Tracker, version 0. String Tracker is a package I use to demonstrate the value of string indexing in collections, so you'll see a lot more about this collection in that lesson. But essentially, I want to keep track of the list of strings that I've used. It's a resource tracker. And I want to know, is this string in use? Pass in that string, return true or false. Mark a string is being used, add it to my list. I've got a list of string names indexed by PLS integer. To mark a string as being used, I add it to the list. So I simply add it sequentially. I call count, add 1 to it, and that gives me that adds it to the end of the list. So I build up my list of elements. And then if I want to find out if a specific name is in use, I pass in that name, and then I have to iterate through my entire collection looking for a match. Get the total number of elements in my collection, get the first element in my collection. Do I have a match? Not yet. So, while I haven't found a match, and my index is not at the end, see if the next element in my collection matches my value. If so, stop. Otherwise, go to the next index, and then return true or false. So this is a very small program, but it demonstrates the fact that I have to do all this work to find an element by the element value, because in this case the sequential indexing doesn't help. And this is the kind of processing that can make your applications run quite slowly as the collection gets bigger and bigger and bigger. So sequential filling of my collection, iterating through my collection, looking for a match. And that's the problem that can occur in our code. So, taking advantage of non-sequential indexing. So associative arrays can be sparse. And certainly, any string index collection is not sequentially filled. So generally speaking, when we talk about the sparseness of associative arrays, we're talking about integer indexed collections. And the neat thing about associative arrays is that the valid value for an index value, is a very wide range of integers, essentially about 4.3 billion values. Now, the reason I know that, and the reason it works that way, is that the associative array indexed by type is indexed by binary integers. I'm going to show you the standard package, which is one of the building blocks of the PLSQL language. It has within it lots of the base data types of the PLSQL language and much else. For example, number. Integer is a number with nothing to the right of the decimal point. Binary integer is an integer with a specific range of values. -2 to the 31st plus 1 to 2 to the 31st minus 1. The index of an associative array has to fall inside this range of about 4.3 billion values. Well, that's an awful lot of values. It's not unlimited, but it's an awful lot. And the main thing to notice here is that oftentimes primary keys in our tables are sequence-generated integers. That's very common in the Oracle world, and usually, not always, but usually, they will fall within this range. In other words, primary keys not exceeding 2 to the 31st minus 1. Now you can take a look at your own tables and see, do I have tables that match this criteria? If you have a table with 25 billion rows in it, well, this probably won't work. But for smaller tables, still large, but smaller tables, the primary key could fit within this range. But primary keys are often not sequentially allocated. Of course, rows can be deleted and so forth. So, combining these features, the fact that associative arrays can be sparse, and that you have a very wide range of integer values to use for your collection, you have a relatively powerful, meaning fast, and simple mechanism for emulating relational table keys, and that's what I want to focus on for the rest of this lesson. But first of all, let's take a look at the process of populating a collection of records sequentially, just to reinforce how that works. This is a script that I showed you when we were looking at associative arrays in the working with associative arrays lesson. What I've done is create a collection whose type has, the element of whose type has an employee's record in every single element, indexed by the primary key, the integer value. Well, or indexed by integer anyway. This one collection can be used for sequential filling of a collection and non-sequential filling. Here's an example of sequential filling. Get me every row in the employees table, assign that record to the employees collection, and fill it sequentially. So start with count of 0 plus 1 is 1. Count 1 plus 1 is 2, 3, 4, 5, 6. So this kind of code will sequentially fill the collection from index value 1. And in this case, the last is always equal to the count. Here's an example of non-sequentially filling my collection. For every employee in my table, take that record, put it in my collection, and use the primary key as the index value. Now, it could be that my indexes are sequentially allocated. It could be that they're not. It doesn't matter. The point is that I'm using the primary key as my index value, which means that if I have the primary key, I can go right to this location in my collection and return the record. So that's the difference between sequential allocation and non-sequential allocation, essentially emulating the primary key. Let's see the point of this. What's the point of it? What good does it do me? So for those tables in which you have a sequence-generated integer value or any kind of integer primary key, and the value does not exceed 2 to the 31st minus 1, sorry, that should be minus 1, then you have the opportunity to emulate that primary key inside your collection. Let's take a look. So in the emulate primary key 1 script, what I've done is create two different packages that provide different ways of looking at the contents or retrieving the contents of the employees table. My first package does basically a traditional lookup. Every time I ask for the row of information for a given primary key, it looks up all the data in that row and returns the single record. So if I call this function 25 times in a minute, it'll execute the query 25 times. Now suppose that for my application the employees table is static. Suppose, for example, it's a materialized view. The data doesn't change when the users are accessing the data. Now in this case I have an alternative. Since the data is not changing, what I could do is take a snapshot of it, load it up in a collection, and then access it that way. Here's how I might go about doing so. Here's my employee lookup 2. I again have a one-row function, pass in the primary key, return the record of information for that primary key. But this program, this one-row function, doesn't look up the data from the database and return it. Instead, it looks up the data from a collection. What collection is that? Well, this collection is a table of rows from the table. So it's a collection in which each element has the same structure as the row of a table. It's a collection of records indexed by integer. And what I'm going to do is use my initialization section of my package to load up that collection. So get me all the rows in the employees table, take that record, put it in my cache, use the primary key as the row number, the index value. So just like you saw in collection of records, this is an example of non-sequential filling, essentially the emulation of the primary key. And then my one-row function doesn't query the database over and over again. It simply goes to that location in my cache and returns the record. Since I've indexed by the primary key, if I have the primary key, I just go to that location directly and retrieve the data. So clearly, it's a lot less code than running the query over and over again. Let's explore the benefits from a performance standpoint. So I'm going to create these two packages. Let's make sure they compile without any errors. You never know. Looks good. Okay. Emulate primary keys 2. So the second script runs a test of the performance of these two different approaches. I'm going to use the sftimer package, which allows me to start up a timer, run some code, and then show the elapsed time down to the 100th of a second. So I'm going to do 100,000 retrievals of the same row of data, the employee data for employee ID 138, using my associative array cache. Then I'm going to do the same thing, 100,000 lookups, using my traditional query every time approach, database table lookup. Then, just to get a sense of the raw power, the efficiency of working with collections, I'm going to populate a collection with 1 million rows of data. And then I'm going to retrieve all the elements one by one. And we'll just see how long that takes. So I run my script. Should take about 4 and something seconds. on 11.2 anyway, and here are the results. The results are pretty impressive. Actually, let's just look at the last run. I've done this more than once. So, it took 4 seconds, over 4 seconds, to do 100,000 database table lookups. That's pretty quick. But check this out. The associative array cache completed 100,000 lookups in 0.06 seconds. The same number of lookups, the same data returned, but because I had the data sitting inside my collection, I was able to access it much, much faster than querying it from the database. That's essentially the power of PGA versus SGA caching. And notice I was able to do 1 million associative array lookups, 1 million iterations through the table, getting data in 0.12 seconds. So working with collections generally is very fast. And if you can find a way to have an alternative index, a way of indexing the data in your collection, to retrieve it using your primary key, for example, rather than querying the data with every single iteration, with every single retrieval, you can get much, much better performance. So that's an example of the power of emulating a primary key inside a collection. Useful only if the table is static during the duration of time that you're accessing the data. And also, of course, if you have an integer indexed key. Now let's take a look at multiple indexes on a collection. So, going back to the model of relational tables, most of these tables do have multiple indexes, and in fact, sometimes multiple unique indexes used to optimize query performance. What if I need to do the same thing in a collection? What if I have a collection filled with all the employee information, but I need to access it in different ways? Access it by name, access it by employee ID, and so forth. You can only have a single index on a PLSQL table, on an associative array. There's only one index by clause. But what you can do is create other collections that serve as indexes into the original collection. So it's the same concept as saying create index on table for a relational table. But in this case, you're going to create other collections and populate those collections that serve as indexes into that original collection. Let's take a look. Now in this case, what I've got is a table called books. And I basically keep track of all the books that I'm planning on reading, my summer reading list. Now a book is indexed by the primary key, the book ID. It also has a unique index on the ISBN number, which is a unique string actually that identifies every book published in the world. And also for my purposes, an author title is unique. So I have 2 unique indexes. I have 1 primary key. And I want to be able to look up information by any of these approaches. And I want to do it in a PLSQL array because I want to look up this information super fast. So I've created 3 functions to look up my data. Look up a book by its primary key. Look up a book by its ISBN number. Look up a book by its author-title combination. So in this case, what I'm going to do is create 3 collections. My first collection is a table of records. All the books in my table are loaded up into my collection, indexed by the primary key. This is essentially the same thing you just saw with my employee ID, my employee primary key emulation, right here. So load up each employee indexed by primary key. So that's my first collection of records. My second collection of records is the ISBN indexing. And in this case, what I'm going to do is create a table of, or collection of, book IDs, primary keys, indexed by the ISBN. It's a string index. And my third collection type is a collection of book IDs, primary keys, indexed by the author-title combination. Now, let's take a look at my load process, my load arrays. Now, what you saw in the previous example was loading up a single collection of employee IDs indexed by the primary key. What I'm going to do here is for every row in my books table, I'm going to take that record, put it in the books list using the primary key. So that's the same thing you just saw. That's emulating the primary key. Now let's take a look at emulating the unique indexes. For the by ISBN and by author title, my 2 other collections, I'm going to take just the book ID, the primary key, and I'm going to store it in my by ISBN collection using the ISBN as my index value. Same thing here, book ID, and the index value is going to be the author-title combination, which is constructed by a function that always puts a delimiter between the author and the title to guarantee uniqueness. So, This collection has every full record in it. These two collections have just the primary key. Now let's take a look at my lookup programs. Here's my OneBook function, passing the primary key, return the book record. And as you saw before with employees, I can pass in the book ID, go to that location in my array, and return the record. Boom. Very quick, much quicker than querying the data from the database. Great. But what if I have the ISBN number and not the primary key? In this case, and we'll skip this reload stuff, you can take a look at all the additional nuances of this package when you'd like. I pass in the ISBN. I want to go to and return the entire book record, but the ISBN list doesn't have the entire record. It has the book ID. So first I get the book ID by going to that location in my by SBN collection, return the primary key. Then I use the primary key to look up the full record. And of course I could just take this and put it right here. So look up the index value, use the index value to look up the primary key, use the primary key to return the full record. Same thing with author title. Go to the by author ID collection, look up the book ID, the primary key, by the author title combination, and then use that to retrieve the full record. So hopefully you can see that what I've done is create two other collections. I've created two other collections that emulate the unique indexes on my relational table, allowing me to look up information very, very quickly, either by primary key or by unique index value, out of my collections, rather than out of the relational table. So that's the general idea, and that's one example of it. Take a look at the GenAA script if you ever want to do something like this. So let's suppose you get excited about this idea. You do want to create multiple indexes in your collection, and you want to create them for every unique index in your relational table. You don't have to write all that code yourself. The GenAA procedure is a program you can use that will generate such a package for you. It essentially, and it's a great example of a code generator, it takes all the information out of the data dictionary for your primary keys and your unique indexes, and it generates a package somewhere down here. It generates a package that creates the functions to retrieve the data, creates the collection types. Here's the one row by for each of my unique indexes. It will create a package for you that will do everything you saw in my little book manager right here. So if you like the idea, if you need to be able to access your collections in multiple ways, if you want to emulate your primary keys and your unique indexes, do not write all of this code yourself. Call the GenAA program, and it will do all the work for you. And that's in the demo zip. So key lessons and a look ahead. Now remember that associative arrays are PLSQL only constructs. They can only be used in PLSQL blocks, but partially because of that, they have a lot of flexibility that's not available to nested tables and v-arrays. You have an extremely large range of values that you can use, both positive and negative. You can choose integer or string indexing. And collections can be sparse. Associative arrays can be sparse, which means that you can easily emulate primary key and unique indexes, construct different ways of getting at the same data in that core collection, and get an incredible boost in performance. Next, I'll talk about taking full advantage of string indexing of associative arrays, another relatively advanced topic for associative arrays. I hope that you found this lesson of interest and can apply it in your own code to greatly improve performance of lookups of data in underlying relational tables. Happy PLSQL coding!